This class, we'll talk about the mediator pattern. The mediator pattern helps us manage complexity in a large production system. You might say that all design patterns are basically there to help us manage complexity in our production systems. However, the mediator pattern is explicitly for this. If you think of how a complex system is built up, typically you'll have a whole bunch of these logical units or classes, and all of them have interactions with other classes. Now, if the classes directly interact with each other, you might find that there's an explosion in complexity, and you just can't manage these dependencies and these interactions. That is where the mediator pattern comes in. Basically, building up these dependencies via a mediator helps keep it manageable. Now, before we dive into the mediator pattern itself, let's take a quick detour on the various ways in which logical units can be built up. First, with the decorator pattern, which uses a chained sequence, and then with the composite, which uses a tree-like structure. Once we know how logical units can be built up, we can start talking about dependencies and interactions between them and see how the mediator pattern can help us. Let's take a slightly roundabout path before we speak about the mediator pattern. Since the mediator pattern exists explicitly to manage dependencies between objects, or rather manage interactions between logical units, it'll help to look at how the decorator and the composite pattern build up logical units within themselves. And then finally, we'll see the mediator. In general, we use the decorator pattern when we have a whole number of objects. Each of these objects have a specific behavior independent of all others. Each of these objects decorate what is passed into them, and this decoration is independent of other objects. Right? Each class in the decorator pattern can be constructed from an object of the common interface or the base class. So you have one class which belongs to the common interface or the base class. You pass that into another and you can create the second. You pass the second into the third to create the third. You pass the third into the fourth to create the fourth, so on and so forth. Decorator objects, the way you use them is by chaining them together. And every link in this chain should not know of the details of the other objects in the chain. They are completely independent. They know their own behavior. They know what they need to do. They don't really need to know what others are doing. They have a common interface or abstract base class and have one class for each independent type of behavior. So all these objects in the decorator chain have a common interface or abstract base class, and the implementation of the class defines the specific behavior for each class, the specific way in which that class decorates. Alright, this is best understood using a diagram, so we'll quickly see one. This is how working with a decorator looks diagrammatically. So we have the file input stream, which is passed into a buffered input stream. And if it wasn't obvious to you already, this is how we deal with file I/O in Java. The buffered input stream is then passed to a gzip input stream. Especially if the file is zipped, this is what you need. The gzip input stream is passed to an object input stream because we've serialized an object. So here we have a whole bunch of objects, each implementing the input stream interface. Think of each of these layers as the layers of an onion. They are all onion, that is, they implement the input stream interface the same. However, they are different in that they specify different behaviors. The objects are created in a chain from one object that's passed in. The user only deals with the outermost object. That's all the user is interested in. In this case, it's object input stream. This diagram sums up the decorator pattern. there is one important thing to remember as a part of the decorator pattern. And that is that all these chained objects, the object input stream, gzip input stream, and so on, are independent of one another. They do not depend on each other for any information or anything else. Now, instead of this being true, what if you wanted a set of objects which look like this? We're going to draw this up really quickly, and soon a structure will emerge. So you have a whole bunch of logical units. They seem to have some kind of inheritance pattern going on. What if we had objects which looked like this? The decorator pattern is essentially useless here. It's not really a chain of objects. There are a whole bunch of interrelationships. The first reason is that the classes are no longer independent of each other. They're dependent each other in a multitude of ways. Also, the user here needs to interact with each of the objects. So the user not only interacts with each of the objects, the user also needs to interact with the structure as a whole. Both of these should be possible. The user needs to interact with all the classes, not just the outermost one. Again, nothing like the decorator. However, there is still one feature in this setup which makes it incredibly useful to us, which is what we'll use. And that is, every object in this hierarchy, every object in this setup are created from objects which are like themselves. That is, every object in this structure has the same interface or base class. They are all like each other. This is pretty much the composite pattern. The composite pattern forms the basis of most user interfaces that we build. UI frameworks generally tend to follow the composite pattern because it fits so well with what they want to build. The whole UI containers in Java is nothing but the composite pattern. But what if our classes did not have a natural hierarchy at all? What if they weren't trees? Neither were they kind of linked objects. If you have no natural hierarchy, how do you deal with these classes? Let's consider a simple UI application which looks like so on screen. It's very simple. It has just two controls. The first control is a button, and the second is a display area. So we have the button which says click me, and that affects the display area, which on clicking the button says hi there. So the button basically updates the display area, the text box, when it's clicked. A very simple interaction, not really part of any hierarchy. In this user interface, the relationship between the display area and the button is basically that of peers. The text box and the button are peers. They are not really in a tree structure or anything like that. However, they clearly are connected to each other in some way. Because they are working together, they do have a connection. However, in the ideal case, they should not directly depend on each other. You shouldn't hold within button the knowledge that it has to update the text area, and the text area should not know that it's being updated by the button. They should not directly know of each other's existence. Why is that the case? Why shouldn't the text area and the button know of each other? In this example, we just have two UI controls, a button and a text area. Very easy to manage. If the number of UI components is huge, and it can easily be so, and they all dependent on each other, the resulting classes would be very tightly coupled. So you'd have a whole bunch of these very tightly coupled classes, all of whom know about each other. Tightly coupled, generally a bad idea, and we'll see why. A way to imagine tightly coupled code is something which looks like this. Does it look familiar? Yes, this is a jigsaw puzzle. The pieces in it fit exactly in one way. In general, tightly coupled code is a very bad idea because it leads to this kind of architecture where all the pieces in our system fit together in exactly one way. And if anything moves a little bit, the whole system doesn't perform correctly. There'll be a mismatch. Jigsaw puzzles where pieces fit in only one specific way is a bad idea. In such a case, code reuse is very hard, and so is adjusting to changes in system design. Since one part fits in exactly one place, it can't be used anywhere else. Loose coupling is always far more preferable to tight coupling. In general, the kind of code we want to write is where all our units are loosely coupled. Now, in the normal course of events, we don't really write code this way. This is how we write code. Let's set up this UI with 2 buttons and 2 text boxes. And let's see how they interact with each other. The way these buttons and text boxes interact is how we write our code, and it's not in a jigsaw puzzle kind of way. So there it is. We have one button and a text box, another text box and a button. There is this frame which contains all of this. It's also the frame which holds all the interactions between these UI components. All interactions between all these UI controls are basically funneled through this frame. It manages all these interactions, and essentially the button doesn't need to know it's acting on a text box or another button. They're completely independent of each other. This is a classic example of the mediator pattern. It's this frame which acts as the mediator, so none of the individual UI elements need to know about each other. They all live independently, fire the events, and the mediator mediates the interactions. The UI elements are referred to as colleagues. They are peers, with all of them of the same importance and not knowing about each other. They are colleagues. The mediator pattern is actually pretty awesome because the colleagues are entirely decoupled from each other. Now, you'll say, this is how I write code. And that's right. You do write code this way. That's because the mediator is another one of those design patterns whose idea has become so widespread that we use it without really thinking about it. The mediator pattern is a part of our programming life without us realizing it.